A positive times a positive is positive, and a negative times a negative is also positive, and 0 times 0 is 0. So one would think that it's not possible to have any solution to x squared equaling -1. In the set of real numbers, that's true. There is no solution. But let's be trailblazers and let's make up a new number. The square root of -1 will exist. And we can then set up a whole system around this base number. And because it's a little bit clunky to always write square root with a -1 underneath it, let's give it a shorter notation. It's very common to call this new number, square root of -1, I. If we then do all the regular arithmetic operations that we've already done on real numbers, multiplying, adding, subtracting, dividing, we can do that involving this new number, the square root of -1, and that's actually how we create our whole new set of numbers. And we're going to call this new set of numbers involving the square root of -1 as its base number, the set of complex numbers. So here we've created some complex numbers. Notice I've taken I and I've multiplied it by 3 and then added 5.72. I now have a new complex number. I've taken the cube root of 19 and I subtracted the fourth root of 9 and multiplied it by I, and I have a new complex number. I could just take I and multiply it by 5. I could take I and multiply it by 0. And if I add 2, I'll just get the real number 2. Or if I add 0, I'll get the real number 0. So it appears that real numbers are actually part of my set of complex numbers. It's also okay to use fractions and decimals, and it's okay to leave I as its original form, the square root of -1. You don't have to write it as I, but it's usually a lot shorter to use that shortcut notation. I also has other meanings though in some fields, like it means impedance when you're studying electricity. So every once in a while, it might be more convenient to actually use its definitional form, the square root of -1. So as mentioned earlier, the set of real numbers is actually a subset of the set of complex numbers. A general complex number is a real number added to a non-real number that involves the square root of -1, or a plus bi is kind of the common form that you might hear somebody talk about. If b is 0, then there is no non-real part to the number. That non-real part is 0. And that's how we see the set of real numbers as a subset of the set of complex numbers. If b is not 0, then the square root of -1 is part of the number, and those values are considered pure complex numbers. Since complex numbers have a real part and a non-real part, they are two-dimensional numbers. Let's graph some. We have 6 plus 3i. The real part is 6, the non-real part is 3, and we graph it like the point 6, 3, with x-coordinate 6 and y-coordinate 3. You also could have 10 plus 0i. That's just the real number 10, and it falls on the real axis. The non-real part or the complex part is 0. How about 0 plus 7.2i? The real part of that number is 0, and the non-real part is not 0, so it falls on the non-real axis. It kind of looks like it's falling on the y-axis. Or negative 4.5 plus 12i. The real part is negative, the non-real part is positive. It's falling in what we would consider quadrant 2. If the real part is negative and the non-real part is negative, it's going to fall in what looks like quadrant 3, like negative 4 minus 8i. And of course, the origin, the good old 0, 0, is also a complex number. The real and the non-real part are both 0. How we add complex numbers is not going to be very surprising. We've already learned that we add like terms. We learned that when we first started algebra. We also learned it back when we were learning how to add fractions. You can only add fractions with like denominators because you're always going to only add like things together. So if I'm adding two complex numbers like 16.5 plus 3i to 6 minus 14i, the real parts, the 16.5 and the 6, will be added to obtain 22.5, and 3i will be added to negative 14i to get negative 11i. You could also take negative 10 minus 2i, and you could add the opposite, i.e. subtract 8 minus 4i, and then the real parts, the negative 10 minus 8 gives you negative 18 as a real part, and then negative 2 minus negative 4i will be negative 2 plus 4i, or positive 2i. Don't forget about fractions. How you deal with fractions doesn't change. If I have 4/5 plus 1/2 I, and I added it to 2/3 plus 1/2, now notice I didn't write the square root of minus 1 as I, because you don't have to. It's just one of the common notations. So in this case, the 4/5 and the 2/3 are like each other. If you add 4/5 and 2/3, you're adding 12/15 to 10/15, and you get 22/15. And then 1/2 I plus 1/2 I is going to give us I. Or you could rewrite it as 22/15 plus the square root of minus 1. So in general, the real parts get added and the non-real parts get added. To multiply complex numbers, you're going to notice that you're actually multiplying binomials together. So we're going to FOIL like we always learned to FOIL. So 12 plus 3i multiplying 5 minus 8i, if I start the first 12 times 5, I get 60, and then outer 12 times negative 8i gives me negative 96i, and then inner 3i times 5 gives me positive 15i, and then last 3i times negative 8i gives me negative 24i squared. But I squared is negative 1. So notice the 60 and the minus 24 times negative 1, they're now both real. So you're going to combine those real parts, 60 plus 84, because the negative 24 times the negative 1 is positive 24. And then you'll combine negative 96i plus 15i will give you negative 81i. But we started off just FOIL. So when you're multiplying complex numbers, multiply them like you do binomials, and then recognize what are the like terms. Again, life doesn't change in complex number land. When you deal with fractions, you still deal with them the same way. So if I multiply negative 1/4 by 2/3, I get negative 2/12, or negative 1/6, and then negative 1/4 times 3i over 4 will give me negative 3i over 16, and then 2i times 2/3 will be 4/3 I, and then 2i times 3i over 4 will be 6i squared over 4, but you can reduce 6 over 4 to 3 over 2. I squared will equal negative 1, and so the negative 1/6 and the 3 times negative 1 over 2 can be combined because they're both real. And then the non-real parts are the negative 3i over 16 and the 4/3 I. So we'll combine those. Negative 1/6 minus 3/2 is negative 10/6, and negative 3/16 added to 4/3 is negative 55 over 48. So there's my new complex number. So in general, when you're multiplying complex numbers, just FOIL and recognize that the last terms are going to involve an I squared, which will give you negative 1, and that last term will then become real and can be combined with the other real part. The conjugate of a complex number is another complex number that when multiplied by it gives you a real number. So for example, 6 minus 4i will have conjugate 6 plus 4i. Why the sign change is because now when you FOIL, you will get 6 times 6 or 36. You'll get positive 24i, but then the inner terms are going to give you negative 24i, and the non-real parts, the 24i and the negative 24i, cancel each other. Negative 4i times positive 4i gives you negative 16 times I squared, and I squared is negative 1. So you now have 36 plus 16 for 52. You get a real number because the non-real parts cancel each other out. And that form stays the same idea, whether you have clean numbers like 6 and -4, or you have messy decimals. So 5.25 plus 0.85 times the square root of -1 will have conjugate 5.25 minus 0.85i. Notice the square root of -1 is I. So if you multiply those two together, again, you have messy decimals, but the concept stays the same. The 5.25 times itself is going to give you a real number. When you multiply 5.25 by 0.85i, you'll get a negative, and then you'll also get a positive of that same product because of the opposite signs. So the 4.4625i terms cancel, and then 0.85i times negative 0.85i will give you 0.7225i squared. I squared still equal to -1, and so that term becomes a real number, and you can add it to the 27.5625. So even when you have messy coefficients, this idea of a conjugate stays the same. Just change the sign of the non-real part. Division of complex numbers really just involves rewriting the number so that the denominators are real, and sometimes you're really not going to want to bother. But if we do go through the process, suppose I had 24 minus 8i divided by 2i. If I multiply the numerator and denominator both by I, I'm really multiplying by 1, and so I don't change the value at all, and I get 24i minus 8i squared. So remember, I squared is equal to -1, and so -8 times -1 gives me a positive 8, and the numerator is then 8 plus 24i, and in the denominator, I get -2. So then, in this case, we can still simplify a little bit more. 8 divided by -2 is -4, and 24i divided by -2 is -12i. So that looks quite a bit cleaner than what we started with. Now, on this hand, I have 20 plus 5i being divided by 4 plus 2i. You might just want to leave that. It kind of depends on what you're doing with it, but if you are going to go through the process of trying to rewrite it so that you no longer have a complex number in the denominator, we want to use the conjugate of the denominator because you're trying to make the denominator real. So don't use the conjugate of the numerator. You want the denominator to be real, so use the conjugate of the denominator. But I have to multiply the numerator and denominator by the same thing, otherwise I'll change the value I started with. So foiling out the top, I will get 80 minus 40i plus 20i minus 10i squared, and foiling out the bottom, I get 16 minus 8i plus 8i minus 4i squared. Cleaning up the numerator, I will end up with 90 minus 20i, and remember, I squared is -1, the 8i's cancel out, and 16 plus 4, because the I squared turned into a -1, I get 20. Cleaning it up a little bit more, 90 divided by 20 is 9/2, and 20 divided by itself will be 1. So I end up with 9/2 minus 1i, and that does look quite a bit cleaner than our original ratio. Here's an example where you might as well just leave your original expression as a ratio and not necessarily worry about going through the idea of how to divide complex numbers. My denominator is 3 minus the square root of 3i. If I were trying to do that process of let's rewrite this so that the denominator is real and not complex, then I'm going to use the conjugate of 3 minus square root of 3i, which would be 3 plus the square root of 3i. So I would FOIL out the numerator, because remember you have to multiply the top and bottom both by the same thing to keep it equal to what you started with. You get a fairly messy expression in the top. We get 6 times the square root of 5 plus 2i times the square root of 15 plus 3i times the square root of 2 plus the square root of 6 times I squared. In the denominator, we do get a nice clean number. Notice the square root of 3i's cancel out when you FOIL, and I squared is -1, and the square root of 3 times the square root of 3 actually ends up equaling 3. So I do get a denominator of just 6, but that numerator turned out to be, quite a few terms, more terms than what I even started with. So depending on what I was going to do with this value, I would maybe actually just leave it how it originally started. But the point is, the process is the same whether you have clean numbers or messy numbers. You don't really change the process. So now that we have invented our set of complex numbers and they exist, we can actually look at graphs like this parabola that has no real zeros and realize it does have zeros. We're just not seeing them on my real number graph. For example, the parabola 0.5 times x minus 3 squared plus 4 does have zeros. They are the complex numbers 3 plus 2i times the square root of 2 and 3 minus 2i times the square root of 2. Complex numbers actually have a lot of other uses. For example, they can help program in higher dimensions. And all we did was create one new number. We created the square root of -1, and out of that created a whole huge, infinitely large set of numbers that actually already contained our infinitely large set of real numbers. So a lot can come out of thinking outside the accepted box of norms.